because of the agglomeration of the CDS particle on the top of the CDS. And here it is clearly visualized. And here the scale bar it is 300 nanometer. And here we observe that with a number of increasing cycle, whatever porous area it is there, it is not actually surface area, porous area between this whatever. Porosity decreases. Porosity between this whatever empty area it is there, it is decreases with increasing number of cycle because it is filling whatever empty space between this TiO2 it is there by using CDS. Now, still here we cannot say whether which is TiO2 and which is CDS. It is not so clear, right? So what we have done high resolution SEM image, and here you can see that this is a TiO2, right? And here dark and bright contrast, you can see this is CDS particle. But still, I am not confirmed this is CDS or not, or this is TiO2 or not, because this scale bar it is 30 nanometer. So what we have taken TM analysis, transmission electron microscopy analysis, right? And here you can see that this is one ball, it is there, right? And here on the top of this ball, you can see this is dark fringes. This is 1, 2, 3, 4 like this one, right? Means these are the dark fringes, means what dark patterns are there on the top of this bigger ball. This is a CDS coated on the bigger wall of the TiO2. This is CDS. This scale bar it is 10 nanometer, right? This is a CDS which is coated on the TiO2. So by CIRAR you can say that CDS it is possible to coat on the another material, right? Like a TiO2 you can coat with the CDS. But still I am not confirmed whether it is CDS or TiO2. So I should confirm it. So how to confirm this one? We can confirm by using high resolution transmission electron microscope. So what we have done, we have taken, this is high resolution transmission electron microscopy. It is 5 nanometer, it is there, right? So how to confirm that one? Just visualizing this one, it is very difficult, which is TiO2 and which is CDS, right? So this is 5 nanometer scale bar, it is there. And you can see some lines are there, right? And these are the atomic planes. These are the atomic planes are there, right? So what you have to do, you have to calculate the interatomic plane distance, that is D, right? That is D sin theta equal to n lambda, right? That D we have to calculate. Interatomic spacing by using Fourier transform, it is possible to calculate exactly, right? Then it is possible to calculate. So here you can see that, now you can see, right? This bigger ball it is there, this bigger ball having some planes in only one direction, certain plane in only one direction. And the smaller balls are there, this one, right? Which is having planes oriented in a different direction. This is one direction, this is one direction, this is one direction. And you can see the beauty of this one. This is whatever this ball size, whatever 3-4 ball size it is there, it is same. Means whatever size of the particle which is deposited on the TiO2, it is same, right? But here you can see two particles agglomerated to form the bigger one, right? This is also 5 nanometer, this is 6 nanometer, this is about 5 nanometer, right? But here some particles are agglomerated, right? So how to confirm again? We can take, here you can see in this mode, you can see that once again I can play, this is TiO2 and then smaller balls are CDS. Now in that one I have zoomed that one so that you can calculate the interplanar spacing. It is about 0.24 nanometer and it is 305 plane of the CDS. And for this bigger part, 0.34 nanometer, right? Very difficult to judge because this is 0.34 nanometer, this is 0.24 nanometer, just 0.1 nanometer difference is there. But you can use the Fourier transform analysis so that exactly you can calculate interplanar spacing. 0.34 nanometer is, it corresponds to 101 plane of the TiO2, that is Anata's TiO2. So here you can confirm that on the bigger ball of the TiO2, that is 25 nanometer Digosa, you can cover CDS by using simple CIRAR technique, and the size of the particle it is also controllable. This is about 5 to 6 nanometer, right? That is the beauty of this one. Now the application part. Here you can also see that titanium it is there, right? Sulfur it is there and cadmium it is there. And this copper it is from the copper grid, where we have dispersed this titanium coated cadmium sulfide, titanium oxide coated cadmium sulfide on the copper grid for the HRTM analysis. So copper grid it is there. Now here, what is the energy band diagram? This is TiO2. CDS, it is having conduction band higher than the TiO2, valence band higher than that of the TiO2, and we are using liquid electrolyte. This energy band diagram has to be fulfilled. right? And then we have done current density versus voltage characteristics, and we have calculated current density, VOC, fill factor, efficiency, RS, RSS, flat band potential, surface area, and we observed the efficiency with increasing cycle, it is about 0.6%, right? And you can think that CDS, it is a 2.42 band gap, right? With the decreasing particle size, the band gap still increases. Still, it shows the efficiency about 0.6%. It is not so bad, right? It is a very good result. And this we have published inside the RSC Advances, very good reputed journal. That is solution process CDS quantum dot on the TiO2 for the solar cell application. So here you can be acquainted with the CIRAR technique, very simple technique that you can adopt in the laboratory. You can start to work with the quantum dot very easily for different inorganic material. Not only two material, not only one compound, more than one compound also, it is possible to deposit by using this technique. Very simple. Also, whether only TiO2 or whether this zinc oxide it is utilized for the solar cell application, or can you utilize other material as well? Right. In the morning, you ask somebody asked that only TiO2 or zinc oxide, why not other material? Right. So here you can get certain answer. Efficiency is not so high, but at least we can get certain answer whether we can utilize or not. So here we have utilized CDS nanowire on which we have coated the dye, and we have used for the solar cell application. That is dye sensitized solar cell based on CDS, not TiO2, not zinc oxide. And the CDS we have deposited by using chemical bulk deposition, just I discussed in the morning. Right. So this is cadmium hydroxide initially we have used, then converted to the CDS nanowires. This one and this nanowire with a very high surface area we have utilized for the dye adsorption. So what we did, this result it was published in the Journal of Biology and Compound. We have glass, we have FTO, we have compact CDS. Again, we have nanoporous, that is nanowire of the zinc, cadmium sulfide, on which we have coated the dye. And we have used two type of dye called rose bengal and rhodamine B, and then liquid electrolyte. And then we have completed the device, right? And this is done by my MSc project student Ankit Tripode, and it was published also inside this journal. And so this is just the outcome of the MSc project. So here you can see this is the surface morphology of the compact CDS, on which we have covered with the nanowires of the CDS. And here you can see that at the 100 nanometer, if you enlarge this one, these are smaller nanowires which agglomerate together to form the bundles. But still you can see there are some cracks, right? So it is whatever wires it is there, also there are pinholes. But because of that pinholes also, it is advantageous because you can get very high surface area. When porosity are increasing the surface area, that is advantageous for the dye adsorption. That is very useful for the solar cell applications. Now, what we have done? So here you can see that different things we have done. That is, this is A, it is there. That is CDS nanowire, it is there, right? Then whatever ethanolic solution of the dye that we have used, and then we have adsorbed on the cadmium sulfide nanowire. And here you can see that this is CDS, this is rose bengal, which is adsorbed on the CDS, and this is rhodamine B, which is adsorbed on the CDS. But here just remember the CDS, it is in the nanowire form, right? It is not the nanoparticle. Here length is not restricted, but diameter it is restricted. Diameter about less than 100 nanometer, but length is not restricted. Length is longer one, right? So that is the beauty of this CDS. Then here, whenever you are working on the dye sensitized solar cell, just I mentioned, you have to think about the energy diagram. This is FTO, this is CDS, then dye for the rhodamine, right? Then electrolyte, what type of electrolyte that we are using, and platinum, it is 6.3435 electron volt, right? So this should we have at the lower side, then it will work very well, right? This is for the rhodamine, this is the rose bengal, right? And this is the IV characteristics of the solar cell that we fabricated under the standard condition. And here we observed the efficiency for the rhodamine about 0.12, and for rose bengal also it is about 0.125. So not much that much difference it is there, because it is having little bit closer absorption region, right? Both dyes are having closer absorption region. So efficiency is not so high, but still the CDS which is coated with the dye, it works very well for the solar cell application. Then this is the next part, whether the CDS nanowire, I have shown you the core shell morphology, like for CDS HGS that we have utilized for the supercapacitor application. So why not to thought, can we fabricate CDS nanowire to form the heterostructure with the another material? So CDS it is N type. When there is a formation of the heterojunction, when the both the materials are of the different type. One is N type, another one is a P type. But this should be heterostructure, not heterojunction. This is a CDS nanowire. It is N type, and Ag2S it is also N type. So it is a heterostructure type of solar cell that we have fabricated, and it is called core shell. So CDS it is core, and Ag2S is a cell on the top of the CDS nanowire, right? And how we have done this one? Very simple thing. So initially, what we have done, we have deposited cadmium sulfide. Cadmium sulfide we have dipped inside the silver nitrate solution. So CDS Ag2S it is having more negative energy of formation. I think 10 to minus 54, and CDS it is 10 to minus 28. Right. So the cadmium gets replaced by silver ions. Cadmium it gets replaced by silver ions, so that there is a formation of the shell on the top of the CDS nanowire. So we have tried, and the reaction it is very fast. Right. So not like a HGS. This reaction we occurred, it is in few seconds. It gets converted to completely to Ag2S. CDS gets completely converted to Ag2S. So we did for 30 seconds, 1 minute, and 2 minutes. Just 30 second dipping, 1 minute dipping, and 2 minute dipping. Here you can see that this is a structural pattern. It is there, right? So here this is FTO, CDS, Ag2S 30 seconds, 1 minute, 2 minutes, and 30 minutes. So we have tried for 30 minutes, right? And here you can see that at the initial it is only CDS, but whenever we are exchanging with the Ag2S, the peak corresponding to the Ag2S is going to enhance. The peak corresponding to Ag2S is going to enhance, and the peak corresponding to CDS is diminishing, right? Now, in order to see clearly, we have taken the HRTM analysis, and you can see that this scale bar it is 2 nanometer, so that you can again calculate the interplanar spacing, so that it can be confirmed that formation of the Ag2S and formation of the CDS, whether it is formed as a core shell or not, right? That we have done by using HRTM analysis. Then this is the surface morphology of the CDS nanowire. This is the original CDS nanowire that we have utilized. This Ag2S is 30 seconds, 1 minute, and 2 minutes, right? And with the increasing the time, immersion time, you can see that the surface gets disturbed, right? So here with the increasing time, you can see that there is an exchange of the cadmium with silver, right? And the particle growth it is faster in case of Ag2S, and you can see that whatever this CDS it is covered, that is CDS core, it is covered with Ag2S as a shell on the top of the CDS, and this forms a core shell type morphology. But nanowire structure it is not disturbed at all. Nanowire it is there, but inside the nanowire there is a possibility of the cation exchange where cadmium ion get replaced by Ag ions, so that you can convert CDS to Ag2S by using simple dipping technique based on the solubility product, that is the negative free energy of formation, right? That is the beauty of this chemical method. Now we have taken the absorption study, right? And here you can see that with increasing the dipping time, absorption age it is shifted towards the higher wavelength side, right? And then we have calculated the band gap. CDS it is 2.42 with 30 seconds dipping of the Ag2S. Ag2S band gap it is about 1.74 electron volt. Ag2S band gap it is 1.74 electron volt. So with increasing the immersion time inside the silver nitrate solution, the band gap of the CDS it is going to decrease, because Ag2S is 1.14, CDS it is 2.42, right? So by coating silver sulfide shell on the CDS, band gap it is going to decrease, right? Once we convert completely CDS to Ag2S, we can get the band gap about 1.74 electron volt, right? So from the optical study also, or from visualization also, you can see the change in the color. CDS it is yellow in color, silver sulfide it is brown in color. So intermediate, you can see the mixed color between the yellow to brown. by just dipping the material inside the solution called silver nitrate. So here that we did some ion exchange, right? And we have studied with the X-ray spectra. So here you can see that AGU test with the 30 second, 1 minute and 2 minutes, right? So here you can, with the increasing immersion time, right, the peak's position get diminished. Means whatever intensity it is get diminished for the cadmium, and for silver it is going to increase with respect to the immersion time. So here you can see that this is for CDS, it is AG, it is there for 30 seconds, 1 minute and 2 minutes. For 2 minutes, it is a higher side, right? So CD, it is going to decrease and AG is going to increase. And this is XPS spectra, it is there, called as a X-ray photo electron spectroscopy, right? So you can have the composition at the 5 to 10 nanometer upper thickness, right? It is possible to locate whatever the elemental composition it is there in terms of the AG or cadmium it is there, right? So depending upon immersion time, whether you are increasing the immersion time, right, silver content it is going to increase and cadmium content it is going to decrease because you are replacing cadmium with the silver ions, right, to form the core shell. Means inside there is a CDS and outside it is a AG2S. Now, this is also same thing that we did for mapping this XPS spectra. Now, we have done this one for the solar cell application, right? And this is the structure FTO, CDS flat, silver sulfide, which is coated on the CDS as a core shell. Then we have used polysulfide electrolyte and platinum coated FTO substrate, right? And this is current versus voltage characteristic. For CDS nanowire, efficiency about 0.1% in the polysulfide electrolyte. Efficiency about 0.1%. But if you are coating with a narrow band gap AG2S, right, and if you optimize this one, the efficiency it reaches to 0.3%. And this here also you can see that this is the external quantum efficiency. The black color it is for the CDS, and whenever you are coating with the silver sulfide, the absorption tail it is there, it shifted toward the higher wavelength side, so that it can be confirm that AG2S shell it can be coated on the CDS material, so that there is a formation of the core shell morphology for the solar cell application. So this result it is published inside the journal, just this published in the recently, that is Journal of Colloidal and Interface Science, having impact factor about 7.5. So it is a very highly reputed journal it is there. Although efficiency it is smaller, but a lot of analysis we have done, and this method that we have said it is a novel method because this is just a room temperature method we have utilized to change the CDS nanowire to the core shell type of molecule. It is CDS and silver sulfide it is a shell. So that this is a core shell type of structure it is there. So next one, it is possible that this is just ion exchange method. So whether it is possible to coat another material on the CDS like bismuth sulfide to form a heterostructure like cationic precursor, ion exchange, anionic precursor, this ion exchange, right? And we have repeated the cycle, and we have changed the number of cycle on the CDS nanowire, right? And this is the substrate, that is CDS nanowire coated on the FTO substrate, right? And this is X-ray diffraction pattern to confirm the Bi2S3 with a different number of cycle, 5, 10, 15, 30. With the number of increasing cycle, you can see that the peak goes on increasing. And this is with reference to the CDS nanowire, right? Then here, this is HRTM analysis